This board is one that we use in the very first amplifier subject. It has one transistor in common emitter mode, and it's set up so that we can change with a large value base resistor. We can change the base current with this pot, and then we can set the Q point at the collector to half of the rail voltage. Then we'll be able to take a measurement after we disconnect the board, take a measurement of the base resistance, and then we can work out the actual base current, and we can compare the base current with the actual measurements that we've taken on the board to see if it all correlates. So we have a nice little lab sheet which is made up for this board. Now, something we're going to do first up with this board is to just have a look at Q1, which is a BC109 transistor. And that BC109, I'm going to flip the board over, and we're going to use the multimeter in a couple of different ways to measure the transistor and confirm that the transistor is in fact serviceable. Alright, so here's my diagram of the transistor, the BC109. It's an NPN, so the emitter is N material, the base is P material, and the collector is N material. And I've redrawn it over here in a very simple way of explaining how transistors sort of work. Well, it's not really how it works, but it's the equivalent diagram to the NP and PN junction which we find inside this transistor. And down here I've got a diagram of our BC109 NPN transistor with its little metal case and a tab on the side and EBC looking up the legs. So we need to know this if we use the multimeter to measure our transistor, because when we put positive potential on the base, negative on the emitter, because it's an NP, we should get current flowing through that junction. And likewise, we do the same thing with the top junction. We'll get current flowing in the forward bias, and if we reverse bias with the meter, then we won't get any current flowing. So let's go ahead and do that. Now I've got the meter connected up across my small BC109 transistor. You can just see that little tab there. So you've got to understand this is looking down the opposite way to what the diagram was that I previously showed. The diagram showed looking the other way up the legs. So the base, whichever way you think about it, is in the middle, and this is the emitter and this is the collector. So there's the emitter giving us a resistance, meaning that there's current being conducted through that junction, and there's the collector also being forward biased and current flowing. And of course, if I short the multimeter leads together, we'll get what's called full scale deflection on the meter. Now, point of interest, this particular transistor is NPN, but I've got the black wire from the multimeter going to the base. So what's the idea behind that? Shouldn't this be a negative potential? I think that we need to have a bit of an understanding about how the multimeter works to see what's actually happening here with our measurement. So let's go ahead and do that now. I've drawn a very simple diagram of what's inside an analog multimeter. We have a 100 microamp, say, full scale deflection, FSD, meter. That is when I've, it's got resting zero down here, and when we've got current flowing through it, the needle deflects to the right and comes up here to full scale. In the multimeter, it can measure voltage and it can measure ohms. So if we're measuring voltage, the switch would be connected to here. We'd be coming through what's called a multiplier resistor, and that would be the positive voltage probe, and that would be the negative voltage probe. However, when we're measuring resistance, I have to move this switch position, and we have a battery now because we are going to put current through a resistive path to cause enough current to give deflection on the meter. And this is what's happening with the transistor, or in fact the diode that we're measuring. We've got the positive on the battery, which has to be connected, thinking in conventional current terms, to the most positive side of the meter. And then the negative side of the battery, if we were to connect the two probes together, which we just did previously, we're going to have a nice current path there, and we're going to get full-scale deflection. But if we put some resistance across here, we won't get quite so much current, and the needle will go somewhere between 0 and full-scale deflection. So this then becomes the negative side of the circuit, and this is the positive side of the circuit. And the red probe is actually the negative polarity in the battery inside the multimeter. And the black probe is in fact the positive side of the battery inside the multimeter. So analog multimeters, when you're measuring transistors and diodes, you have to remember that the black probe is always the positive side. Here's my black probe here, negative probe, and that is always the positive side of the supply inside this simple analog multimeter. In this particular scene, what I've done, I've got the multimeter still connected up in the ohms range, and I've got a digital multimeter next to it connected to the voltage range. And because we just saw that the ohms range in an analog multimeter, we have an internal battery which is supplying current to make the needle deflect. Therefore, we should be able to measure the voltage, the internal voltage in the meter, using a high impedance meter like this digital multimeter. So I've put the black leads together, negative to negative, so to say, and then I'll put the two positive leads together, and there's the voltage in the battery. But, ooh, what's happened? We've got a negative sign here. Negative 1.6 volts. Why is it negative? Because for the reasons we just said, I've put positive to positive and negative to negative. But this is proving that the polarity from the analog meter is actually reversed. I'll go ahead and change that. Alright, I've swapped things over now. Alright, I've swapped things over now. I've got red to black each way. So I've actually got the positive on the DMM to the negative on the analog meter, and vice versa, to measure 1.6 volts DC. Again, proof that the polarity in the leads from the analog multimeter are reversed to what you'd expect them to be. So be very careful with that when measuring diodes and when measuring BJTs, because you certainly need current. They're a current-driven device. You certainly need current to forward bias the junction and prove that the junction is serviceable. Now, what I'll go ahead and do, knowing that this is my positive lead, and this is in fact a NPN transistor, I'll put this on the collector of the transistor, and then I'll use the negative lead and I'll put it on the base. And look at the needle, we don't get any deflection there at all, because we have reverse biased that junction. And that's what we'd expect to get. If the junction was short-circuited, for example, the leads go together, we get full-scale deflection. That's reverse biased, we don't get any deflection, no current flows. We had it forward biased before because we put the positive lead, current speaking, onto the base. In this scene, I have the digital multimeter set up on the resistance range, and then I put the negative lead to the collector, and we'll put the positive lead to the base. Ooh, we know it's an NPN, but we don't get any deflection. Why not? Well, the fact is that this type of meter has an entirely different electronic circuit with virtually no current in the leads, so we don't get enough current to forward bias the transistor. In fact, with this type of meter, we have to select the proper range to measure diodes and transistors. And that's this range shown here with a diode. And using that range now, this actually has a thing called a 1 milliamp constant current source built into it. And by putting that constant current through the junction, I'll be able to measure the voltage drop across the junction. So there's that junction with positive. It's an NPN transistor. Positive is on the base and negative is on the collector there. And I'm measuring 705 millivolts across that junction, which small signal transistors, 0.6, 0.7 volts is exactly what we'd expect to get. Now if I go ahead and I move this across to the emitter, and then we go between the base and the emitter, 713 millivolts. Very similar. You'd expect similar resistance or similar voltage drop in this case, I should say, across each of those junctions. And of course, if I was to reverse bias those junctions by putting this lead onto the base and this red lead onto the emitter, being an NPN transistor, we wouldn't measure anything. And of course, across collector, emitter, in both directions, we won't measure anything for reasons of this simple diagram which we looked at earlier. And there you can see we've got cathode, then anode, anodes connected together, cathode at the other end. So there's no way that current can conduct through those two back-to-back diodes from collector to emitter. If there was current flowing through there, the transistor would be unserviceable. This is a slightly different transistor. This is a BC547. The last transistor we looked at was a BC109. This transistor is, I'm holding it in my hand here, it's a small plastic case, and it's a bit of a different shape to what our little BC109 was. It has this sort of a hemisphere that we can look up the legs there again. So EBC. BC547. It's also an NPN transistor. I've got written here beta 298, and I've already measured the beta of this transistor with a beta tester. And I remember when I did my first electronics training, a beta tester was quite an expensive bit of equipment, but these days a beta tester is something that you buy off the shelf, built into a digital multimeter for about $15 or $20. So let's go ahead and have a look at that multimeter and its HFE or beta test function. For the beta test function, or HFE, there's a set of tables called H parameters. This equates to beta. We have to select this range on the digital multimeter. For this test, we do not use the built-in leads, or rather the external leads on the meter. We need to use this built-in test set of prongs here, which one set is for NPN and one set is for PNP, and they're clearly labelled EBC, EBC. And why have they got 4 in a row? Well, it really, some of these transistors, the pinouts are a little bit weird, and I suppose that's the right word to say it, and trying to get the geometry correct into the meter can sometimes be a bit of a headache. Now, from our diagram before, holding that hemisphere that way and looking at it, it was from left to right, EBC. So I need to orient that transistor correctly, EBC. I know it's NPN, and by plugging it in there and putting some pressure on it, there's 298 is the measured beta for that transistor. That's a very handy thing to be able to use, because if you wanted to match two transistors to have the same beta, that'd be a really good thing to be able to do it with, because I can guarantee that if I go to the drawer and get a handful of these BC547s, the beta's not going to be exactly the same for every one. I might do that later, might be an interesting experiment. So that's about it for measuring the transistors using both the analog multimeter and using the digital multimeter, and working with the very first board that we'll be using in Amplifier Fundamentals subject here at TAFE New South Wales. Don't forget to look at the circuit again and understand about the full scale deflection on the meter, and the fact that we need current to drive the meter movement, therefore we have to have the internal battery. But that internal battery current of course flows out through the leads, and the lead polarity is actually different to the colour, only in the ohms range, only when we're measuring diodes and when we're measuring transistors. So that pretty well wraps that up. This has been Greg Moore for TAFE New South Wales. I hope that was good.